Welcome to this video on the Fourier transform. By the end of this video, you will be able to Fourier transform a function analytically. Okay. Now, what is the Fourier transform? Recall interpolation, right? For interpolation, we find a function that gives data points exactly, but then we use this function to evaluate the data in between data points. And the functions we've used so far for interpolation were polynomials, right? They were this general kth order polynomial. But let's do something else, right? They don't have to be polynomials for interpolation. Let's use sinusoidals. So that would mean that my interpolation function, if I write this as a function of t, would be some constant a naught plus the sum from 1 to infinity of an amplitude a sub k times the cosine of k omega t plus the sum from k equal 1 to infinity of an amplitude b sub k that multiplies the sine of k omega t. Now let's do some assumption and some simplifications and introduce some definitions. So I'm going to assume that g of t is a periodic function with a fundamental period uppercase t, which means that the fundamental frequency, uppercase f, is just the inverse, the reciprocal value of the fundamental period. I can then also define the fundamental angular frequency, omega. That would just be 2 pi divided by the fundamental period. And in the formula up there, we have a k, which is the wave number, which basically tells you the number of sine or cosine waves per fundamental period. So for the fundamental period t, which is uppercase f or omega, if k is equal to 1, I have exactly one wave, one sine or one full cosine in the fundamental period. If my k is equal to 2, I have two waves. If my k is equal to 3, I have 3 waves in the fundamental period, and so on. Now the task for the Fourier transform is given the functional form of g of t, right, that I am going to use, find these amplitudes, a naught and ak and bk. Okay, and that's what we call the Fourier transform. Okay. Now, if we have an analytical function given that we want to do the transform on, then we call it the Fourier transform. But if our function is only given by discrete data points, so some tn and fn, and we want to find these amplitudes ak, bk, then we will call this the discrete Fourier transform. Okay, so here is my functional form, g of t, right? I'm just going to copy this down here. And the task now is to find these a and b values. So what I'm going to do to find them is I'm going to integrate over the fundamental period t. So every term in this equation up there for the definition of g of t, I'm just going to integrate from 0 to t. So I'm going to throw individual integrals into this equation. And the ak's and the bk's in those sums, right, can be moved outside of the integrals because they're not a function of t. Okay then. So here I have the integral from 0 to t of the cosine of k omega t dt. And k is a integer number, right? It's a positive integer number. So now, what is this integral? Right? If I'm integrating this, the cosine, I get 1 over k omega times the sine of k omega t from 0 to t. But with the definition of the fundamental angular frequency, omega, I find that t is equal to 2 pi over omega. So those are my integration bounds. So let me substitute them in. So I get 1 over k omega times the sine of k omega times the upper bound, so 2 pi over omega, minus the sine of 0. Well, the sine of k times 2 times pi, where k is a positive integer number, is always the sine of a multiple of 2 pi, which is always 0, and the sine of 0 is 0 as well. So this integral is 0. It drops out. So this entire sum there is just 0. Okay, next up, the integral from 0 to t of the sine of k omega t. Well, if I integrate this analytically, I get that this is 1 over k omega times the cosine of k omega t between the integration bounds of 0 and t, but t is 2 pi over omega. So that's negative 1 over k omega times the cosine of k omega times 2 pi over omega minus the cosine of 0. So that's minus 1 over k omega times the cosine of, well, what's this? Well, it's the cosine of k times 2 pi. That's always 1, right? A multiple of 2 pi, the cosine is always 1. And the cosine of 0 is 1 as well. So I have 1 minus 1 in the square parentheses here. So that's always 0 as well, which means all of those sum terms over there on the right are 0 as well. So the only thing that's left is the integral from 0 to t of a constant a naught dt, which is, well, it's, if I can solve this, right, it's a naught times uppercase t, and I can just solve this for a naught. So a naught is 1 over the fundamental period times the integral from 0 to t of g of t dt. So if I have a g of t given in some analytical form, if I integrate it from 0 to t, that would be, and divide by t, the fundamental period, that would be my a naught. Okay, so I found my a naught. In order to find the AKs, so the amplitudes that multiply the cosine, I'm going to do a trick. I'm going to multiply both sides by the cosine of m omega t. And then I'm going to integrate again from 0 to t. And m is some whole integer number that's positive. Okay, so that gives me what? Well, the integral of g of t times the cosine of m omega t dt is equal to the integral of a naught times cosine m omega t dt plus the sum, I can pull out the ak, times the integral from 0 to t of cosine k omega t times the cosine of m omega t dt, plus that sum term where I pull out the bk times the integral of from 0 to t of sine k omega t times this cosine of m omega t dt. Now, let's recall from trigonometry that, or the property of trigonometric functions, that the integral from 0 to 2 pi of the cosine of k theta times the cosine of m theta d theta is either 0 or pi. It is 0 if m is not equal to k, but it's equal to pi, this integral, if m is equal to k. Now let the theta be, in this formula, omega times t. So that means that the d theta is equal to the omega times dt, which means that dt is equal to 1 over omega d theta. And my omega was 2 pi over the period. So then that means that my d little t is the fundamental period divided by 2 pi times d theta. Good. So let's integrate what we have in this large sum formula over there. So let me calculate what is the integral from 0 to t of cosine k omega t times the cosine of m omega t dt. Well, first of all, the dt was fundamental period divided by 2 pi d theta. Okay, and I'm going to basically do a coordinate transformation. I have omega times t is equal to theta, so that would be cosine k theta. And then I have omega t in the other cosine term, so that would be cosine of m theta. And my integration goes from 0 to t, but I do this coordinate transformation that now makes the integration go from 0 to 2 pi. Okay, so now let's use this formula, right? Because I now have explicitly here the same integral. So this is either equal to 0 times t over 2 pi if m is not equal to k, or it is equal to pi times t over 2 pi, so t over 2, if m is equal to k. And similarly, we can apply a similar trigonometric function to the sine of k omega t cosine m omega t. And if we do this type of similar coordinate transformation, we'll find that that is always equal to 0. Okay, so let's apply this. If the sine cosine is always equal to 0, that drops out. And I'm left with what? Well, this term over here, that's pretty much always 0, except for if m is equal to k. So that gives me that a sub k is equal to 2 over the fundamental period. And then I have, well, this a naught times the cosine, but I already saw that before. We saw that that is always 0 as well if I integrate over the fundamental period. Okay, so what have I left? I have left that ak is equal to 2 over t times this integral on the left-hand side. So the integral from 0 to t of g of t cosine of k omega t dt. Okay, so if I have a g of t that's analytically given to me, I just need to multiply it by the cosine of k omega t, analytically integrate this from 0 to t, and that will give me my amplitude ak. Now, to find the b sub k, I basically do something very similar, except that I multiply both sides by the sine of m omega t and then integrate from 0 to t. And the net end result of that is that my b sub k is equal to 2 divided by the fundamental period times the integral from 0 to the fundamental period t of g of t times the sine of k omega t dt. So this is then how we do the Fourier transform. If a functional form of g of t is given and we want to find the amplitudes ak, bk, and a naught, we just have to analytically evaluate these integrals one by one for every possible k value, which goes from 1 to infinity. Thank you for watching.